Here's a number worth sitting with. Of all the plastic ever produced, we're talking billions of tons, only 9% has ever been recycled. Not because we lack the technology to collect it, but because of something more fundamental. Most plastic at the molecular level simply cannot be mixed. This is a polymer problem, and a 2023 paper in Nature proposes a solution built on the same thermodynamics that created it. Think about what happens when you melt polyethylene and polylactic acid together. They don't blend. They phase separate, forming large, discrete domains of each polymer rather than a continuous mixture. And the reason is thermodynamic. For long polymer chains, the translational entropy of mixing is essentially zero. It scales inversely with chain length. So even a weak repulsion between unlike segments is enough to drive the system toward phase separation. What you get is a coarse, brittle material, mechanically inferior to either starting polymer. This is why recycling facilities must sort plastics by resin type before processing. Anything that ends up in the wrong bin gets downgraded or landfilled. The question this paper asks is, what if we didn't have to sort at all? Researchers have tried several routes. Chemical recycling breaks polymers all the way down to monomers. Effective, but energy-intensive, and still doesn't handle mixed streams well. Enzymatic approaches work elegantly, but only on specific polymer types. Closer to this paper's approach, static crosslinkers. These can create a permanent network. Once cross-linked, the material can't be remelted or reshaped. You've traded recyclability for performance. This paper overcomes all these limitations. The Universal Dynamic Crosslinker, or UDC, combines universality and dynamics. A bi-S-diazarine core forms reactive carbines on heating that insert into CH bonds of virtually any polymer, polar, or nonpolar. Between these reactive ends sits an exchangeable bond, such as a disulfide, enabling a Vitromer-like network that can flow and be reprocessed. Mechanistically, UDCs activate under heat, generating carbines that graft onto different polymers and bridge them. These bridges then undergo dynamic bond exchange, allowing the compatibilizing network to grow throughout both phases. The result is true interfacial compatibilization, not just surface adhesion. The result is striking. Electron microscopy shows that untreated PE polyester blends contain large, discrete droplets. Classic phase separation. Adding only 5% UDC during melt extrusion removes this interface entirely. Mechanically, the compatibilized blend achieves over a 10-fold increase in toughness, even for real post-consumer waste streams. And crucially, this works on ternary blends of incompatible polymers, LDPE shopping bags and PLLA cups, colorants, together with no prior sorting. Because the crosslinks are dynamic, the material can be remelted and reshaped repeatedly without property loss. Reprocessed specimens show the same tensile profile as freshly processed ones. This is the critical distinction from chemical recycling. You're not destroying and rebuilding. You're preserving the material value of each component and adding value by making them work together. Despite strong results, several challenges remain. UDC synthesis is currently too costly for commodity-scale deployment. Real waste streams are more heterogeneous than the model blends studied. In addition, scale-up requires full life cycle and techno-economic validation of extrusion and processing at industrial volumes. Dynamic cross-linking reframes the plastics problem. Instead of asking how to separate or destroy mixed plastics, it asks, can we compatibilize them into something better? It turns out the thermodynamic barrier of polymer immiscibility, long treated as a hard constraint, can be chemically engineered around.